I'm here to talk about work today and the relationship between work and energy, because they are very, very closely tied together. So I have a definition of work up here. Work is just force times distance. And we could write that out as an equation. Work is force times distance, basically meaning that you apply a force to an object and you move it a certain distance. So let's say I apply 20 newtons of force. I can make up a mass for this, but the mass doesn't matter because it's really about how far does it go. So if it goes, 6 meters, the work is equal to the force of 20 newtons times the distance of 6 meters, which equals 120 Newton meters. But work, as I said, is related to energy, so it's really just 120 joules. A Newton meter is the same as a joule. Now, there's a second definition I put up here saying it takes work to change the energy of an object. And I can say an object or a system, really. Because whenever you do work, you're adding energy in some way, or you're changing the energy in some way. So let's say you push that block with 20 newtons of force and it goes 6 meters. There's a couple possibilities for what could happen. First of all, if it's frictionless, that means the block is probably speeding up. You're applying a constant force and it's moving, so it would be accelerating. And as it accelerates, the velocity increases. And as the velocity increases, the kinetic energy increases. So by doing work, I have thus increased the kinetic energy of this block. Now, maybe it's not a frictionless surface. Maybe there's friction. Maybe it's moving at a constant speed. So let's say there's friction and it's a constant speed. If there's a constant speed, then kinetic energy is going to be constant. However, you're still doing work. You're still applying a force over a certain distance. Maybe the net force is 0, but the work that you do, the 20 newtons that you do, moving at 6 meters, is doing work. So if it's not increasing the kinetic energy, and it's not increasing the potential energy because it's still on a flat surface, it's not increasing in height, that means that the work is actually increasing your heat, aka your internal energy. So by moving the block, you're doing work, and the work adds heat energy or thermal energy to the system. Now you could actually have something that's a little bit of both. You could have friction that's not a constant speed. You could have friction, but the block is still accelerating. So you're increasing both kinetic energy and heat, which goes by the letter Q, both increase. They wouldn't increase as much as in either of the previous examples, but they would increase. There's other ways to think of work too. If you lift something, for example, lifting, you typically need to use a force that's equal to the weight of the object. F sub g. So let's say you lift this 5 kilogram block. You're lifting it with approximately, if the weight is 5 times 9.8 meters per second squared, that means I'm going to 5 times 9.8 equals 49 newtons. That means you're lifting it with 49 newtons. So you're applying 49 newtons to lift it. If it's going at a constant speed, this might not look like lifting, but it is, trust me. As long as you get a little bit more than 49 at first, you can keep lifting with only 49 because it's balanced and you'd be moving at a constant speed. So maybe you lift it upwards 6 meters, or you lift it, let's do a smaller, 3 meters. The force you're using is going to be equal to 49 newtons, and the height of it the distance it's moving is 3 meters, so you end up getting 147 joules of work you've done. And by doing this work, you've increased the gravitational potential energy of it. And if you were to measure the gravitational potential energy of the block when it's 3 meters high, you would find that the change in gravitational potential energy, mgh, mass would be 5 kilograms, g is 9.8 meters per second squared, and the height is 3 meters. You multiply these out, you find you get the same 147 newtons. So by doing work, you have increased the gravitational potential energy of this block by lifting it up. So work is always going to do some sort of change in energy. And thus, when you see work, often you want to think about energy because they are related. Sometimes they'll ask you to find the work of something, and you don't do it with force times distance. You actually do it with delta E. And this is the equation that you see on the reference table, the change of energy. So if you find the initial kinetic and the final kinetic energy, you can say, hey, I started with 0 joules and I ended with 147 joules. Let me do this. E final minus E initial. 147 joules minus 0 joules. That means you have done 147. I cannot write sevens today. 147 joules has been the change in your energy, so that's how much work you did in lifting the box. Now, there is one other important thing to keep in mind, too. And that is the direction of the work. I do want to point out briefly, too, W stands for work in this, but be careful because work is in units of joules. Just like energy, because joules, work, and energy are directly related. It is not in units of W. W as a unit means watts, which is a unit of power. So don't get those confused. W for units means power, W for a variable means work. Okay, so the one last thing to keep in mind is that work, well, the force done for work needs to be in the direction of motion. And if they are not in the same direction, otherwise you need to use a component of that force vector that is in the direction of motion. So, for example, let's say you are here mowing your lawn with the lawnmower. And this makes an angle of 30 degrees from the horizon. And you're pushing with 50 newtons of force. And maybe the mower moves 6 meters. The work is not equal to 50 times 6. You need to take a component of the force vector that is in the direction of motion. So imagine this is your force vector here, representing 50, and this angle here is 30 degrees. You're looking for the component that is represented by this side right here. So in this case, let's see if the blue. If this is your hypotenuse and this is your adjacent angle, this side is then going to be 50 newtons times the cosine of 30 degrees. So you end up with 50 newtons times the cosine of 30. That is a component of force in the direction of motion. So therefore, work ends up being 50 newtons times the cosine of 30 times the distance that you move, which is 6 meters. So it would be 0.87 times 0.87 or so times 300. Or about 260 joules of work. Meaning you also increased the energy of the system in some way, either through friction or increasing kinetic energy by 260 joules. That is it. Thank you very much for watching.